I'd like to hit up one more topic in the area of energy, and that is the concept of power. Now, power, or average power to start with, is just simply the work done over the time that it takes to do that work. Another way to look at that is the change in energy, change in mechanical energy over the time that it takes to do that. So that is your average power. It's a rate. It is in watts. 1 watt, which we use the symbol capital W for. Somewhat unfortunate because it looks like work, but 1 watt is equal to 1 joule per second of energy transformation. So for example, a 100-watt light bulb transforms 100 joules every second from electrical energy to thermal energy and light. So that is the meaning of a watt. It is a rate, and power, like work energy, is a scalar. Now, as it turns out, there's actually another way to calculate instantaneous power. Let's look at it this way. Power instantaneous, I will drop the average subscript. This is the instantaneous power. What I'm going to do is I'm going to look at it in terms of a very small amount of work over a very small amount of time. So this will be the work done over the delta t, and this is going to be the force times the very, very small delta x. In fact, let's go ahead and use the dot product. It's F dotted on delta x over delta t. That's very small. Now you'll notice that if I make these deltas go down to 0, like as delta t approaches 0, so the limit of this thing as delta t approaches 0 of F dotted on delta x over delta t is what? Well, what is this part? What is delta x over delta t as delta t approaches 0? Notice that that's just the velocity. So, in other words, the instantaneous power can be calculated by F dotted on the velocity at any one time. What is the instantaneous rate of energy transformation? It is that. So let's take an example right here. So here is a situation which I'd like to look at. We've got a car which starts at rest, and there's a force of thrust on it, and that is it's actually the force of the ground on the car. There's got to be an external force, but it's generated by the motor. It's basically the motor turning the wheels, which push on the road, and the road pushes back on the car. But let's just call it the force of thrust, and that's 3,000 newtons. And this thing accelerates. This car accelerates for 10 seconds, ends up at 30 meters per second, and it ends up having moved 150 meters. My question to you is, what is the average power of the motor for the entire motion, and what's the instantaneous power at the halfway point at 75 meters? So there's actually a couple ways we can look at this and try to tackle this thing. If we first look at what is the average power, we can figure that out pretty easily a couple different ways. The average power is the work done over the time, or the change in energy over the time. And in this case, the only type of energy that we're changing, the type of mechanical energy, is kinetic energy. So this is delta K over delta T, and that is going to be K final minus K initial over delta T. Notice the K initial, it starts at rest, so that'll be 0. K initial is just gone. So all I got to do is figure out what is K final over delta T, and that'll give me that average power. And that's pretty simple. It's 1/2 mv final squared over delta T. And to put that all together, we have 1/2 1,000 kilograms. V final squared is 30 meters per second. That's 30 meters per second. Square that and divide it by the 10 seconds. And what you end up with is 500 times 900. Divide that by 500 times 900 divided by 10 is like 50 times 900. 45,000 watts. Now, to make sure that makes sense, let's actually convert it to horsepower. If we got 45,000 watts, to convert, I'm going to use the factor label method. Turns out that 746 watts is 1 horsepower. And when you just do the math here, dividing by 746 there, what you get is that's about 60.3 horsepower, which is pretty reasonable. That's kind of a mid-sized car. It's totally possible though. So 60.3 horsepower is what we get. Now, so you might expect that's the average horsepower. Let's do part B and figure out what the instantaneous power is halfway through our journey at 75 meters right there. So you might think, oh, it's probably half of the power or something like that, or maybe the same power. But none of those things turn out to be right. What we're going to have to do to figure out the instantaneous power is just dot the instantaneous velocity at that time on the force. But the thing is, we don't know this. We don't know what that velocity is. You may suspect, okay, it's going 30 meters per second when it hits 150 meters. It must be going half of that speed. Again, that is an incorrect assumption. Notice that it's going to spend most of its time. Now, it is true that halfway at 5 seconds, it'll be going 15 meters per second, but it'll spend a lot more time going this distance because it's moving slower. So it ends up not being at 75 meters at half the time. In fact, it's much more than half of the time to get halfway. So we got to figure out what speed it is, and it's not 15 meters per second at that time. Let's figure out what that is. We're going to use the Grandmammy equation. V final squared equals V naught squared plus 2a delta x to figure out what that V final is. This is 0. It started from rest, so I just get the instantaneous speed is the square root of 2a delta x, which in this situation, notice it's accelerating at 3 meters per second squared, so it's 2 times 3 meters per second squared. I know that because it's 3,000 newtons of force on a 1,000 kilogram car, and our delta x is 75 meters. When we do all this, we're going to get, notice our units are meters squared over second squared, so that works. And that gives us 21.2 meters per second. So let's figure out the instantaneous power at that moment. It's a 3,000 Newton force. It's dotted on 21.2 meters per second. They're both in the same direction. Gives us 63,600 watts. So we're actually, by that time, we are exerting more than the average power. At that point, doing the same conversion, 85.2 horsepower. Now, just for kicks, I'm going to extend this a little bit. What if we want the power at the last instant of the motion? Power at the last instant. Let's see what that is. Well, we know our force is a constant 3,000 newtons. At the last instant, we're going 30 meters per second, so that is 90,000 watts. And in fact, you will notice that that is, in fact, half, or that half of that is the average power for the time. One last thing, and that is the area under the power time curve, P versus T. And in this case, it is going to go up linearly with the speed, and this last power is 90,000 watts. If you figure out the area under this curve, that entire area right there, that will be the work done. And you can prove that. The work done we figured out from way before. By the way, this will be at 10 seconds. The area under that curve is 90,000 times 10 seconds times 1/2. So the work done is 450,000 joules, which is what we found for 1/2 mv squared anyway. So that makes sense. The area under the PT curve is the work done. And you can also figure that out, by the way, just as a little review, it's the same as the area under the F versus delta X curve, which would be, this force would be 3,000 newtons, and the delta X is, as we figured out before, 150 meters. When you find that area under the curve, it will be the same in joules. Okay, so very last thing is, if you are in calculus, you can actually figure out the net work done by integrating. This is the same thing as finding the area under the curve. P times dt. The integral of p dt gives you the work done, and that's just the area under the PT graph. One last review, that will also be equal to the integral of f dotted on dx. Notice that is a dot product because these two are vectors. These are not vectors, so I'm just going to eliminate that dot product so there's no uncertainty there about that. This is not a vector. You can integrate with it with respect to another non-vector scalar time, or you can integrate the two vectors, but you have to use the dot product. All right, that's it.